Alright, so for this video, we're going to be looking at some scholarship concepts and some scholarship practice questions. So in scholarship, we have the idea of a source moving not directly towards an observer, but instead at some angle. So remember the Vs in the equation, that means the relative velocity of the source to the observer, not the indefinite velocity of the source. So just because a source is moving at, let's say, 80 meters per second, that doesn't necessarily mean that the relative velocity to Kevin or some observer is 80 meters per second. So the Vs always refers to some relative velocity, not the actual velocity that the source is moving at. So that's a really easy, very common mistake that people make, is that they think that, oh, because the source is moving at 80 meters per second, that also means that the relative velocity must be 80 meters per second, and that's not a correct conception to have. Alright, so we wrap example 1. Sorry, the arrow shouldn't be there. Okay, so a plane moving at 188 meters per second at a height of 900 meters from Kevin, who is watching the plane from below. As the plane is approaching Kevin, he hears a changing frequency, though the plane is not accelerating. The waves from the plane have a frequency of 900 Hz. Calculate the frequency Kevin heard when the plane is 850 meters away. Alright, so if we have a little bit of a vector diagram here. Alright, so try this question for yourself. Okay, so calculate the actual observed frequency that Kevin hears given the information in question. Alright, so for this question, okay, so some people might just say the relative velocity of the source to Kevin is 188 meters per second because the source is moving at 188 meters per second. However, that's a very incorrect misconception because that is not the relative velocity to Kevin. That's because there is a certain height between the plane and the Kevin, and the relative velocity is actually that component of velocity traveling in the same direction as Kevin. So the easy way to remember this is when the plane emits the waves, they're circular in shape, and we know that so that relative velocity actually means what direction will the waves travel towards Kevin, because we know that the Doppler effect is heavily reliant on the velocity of the waves. Okay, so we know that. So what I'm trying to say is that the relative velocity is basically the component of velocity that's acting in the same direction as how the waves would reach Kevin. So the waves would reach Kevin through this component, this diagonal component. So waves are circular, we need to find the relative velocity to Kevin. That is the velocity in the direction that the waves will travel through to Kevin. Okay. Alright, so we know that this is our x, our angle x. So we know that tan x equals to 900 over 850. So if we take the tan inverse of both sides, so we'll get x equals to inverse tan of 900 over 850. And that should come out to x equals to 46.64 degrees. And continuing on to this next question. To continue on from the last question. So we know that this angle here, so we also know that this angle must be x. The reason, if you go back to a previous slide, we'll see that the angle x is alternate angles with this angle in the vector diagram. Alternate angles on parallel lines, they are equal. From our level 1 geometry skills, we know that alternate angles on parallel lines are equal. Therefore, this is also angle x. And we know that x, we just figured it out, was 46, was it 46? It was 46.64, and therefore we can now see that the component acting in the same direction as Kevin, so how the waves would travel to Kevin, that component V, the V would be equal to, so cos 46.64 equals to V over 188. So that comes back to our basic Pythagoras theorem. So Pythagoras, cos is A over h, so adjacent is our velocity side we want to find, and h is our hypotenuse, which is our 188 meters per second horizontal component. Rearranging for V, we'll find that our V is 129.09 meters per second. And this 129 meters per second, that is the actual relative velocity of the plane to Kevin. That is the relative velocity, therefore we can use this in our Doppler equation. And we use the minus sign because it's moving towards Kevin. So this component of the velocity is towards Kevin. Therefore, the observed frequency should come out to be 1450.82 Hertz. That will be our final answer. Question B. Explain why Kevin hears a changing frequency even though the plane is not accelerating. Alright, so give this question a try. Okay, so try to think why there's a changing frequency. Just as a hint, the hint is that we have to think about the relative velocity. Even though the indefinite velocity, so the actual velocity is not increasing, think about how the relative velocity is changing for when the plane is away from Kevin or towards Kevin. So just think about how that relative velocity changes as the plane is approaching. Whereas for this question, the Doppler effect can be observed when there is a relative velocity of the source to an observer. Because the plane is flying in the air, we need to take the component of velocity in the same direction as how the waves will travel to Kevin. However, the plane is not accelerating. Even though the plane is not accelerating, the position of the plane is having an effect on the size of the component of velocity towards Kevin. When the plane is very far from Kevin, a greater size of its velocity is acting towards Kevin. Okay, so just think about it. So if the plane is very far away and is heading towards Kevin, a greater amount of that horizontal component would be in the direction of the waves traveling to Kevin. So it'll be in that same direction. There'll be a greater component in that direction, and that means that the relative velocity of the waves to Kevin, the relative velocity of the source to Kevin would also be higher. Therefore, the observed frequency will be increased. It will be much higher if the plane is further away from Kevin. Alright, so I said here when the plane is very far from Kevin, a greater size of its velocity is acting towards Kevin, hence there is a higher velocity relative to Kevin and a higher observed frequency because frequency is inversely proportional to wavelength. The speed of the wave remains the same because it's the same medium. As the plane approaches, the velocity in the direction of Kevin decreases. So if you think about it, the plane approaches, the component there is the angle there is going to get bigger and bigger, and therefore this component is going to get smaller and smaller. So when the plane is very far from Kevin, the angle between the horizontal and that component of velocity is very small, and because it's very small, we can see that the component acting towards Kevin and the horizontal component very, very similar to each other. Okay, especially if it's very, very far away. Let's say it's like 2,000 meters away, then that angle is much smaller, and therefore we'll see that the relative component would also be larger. Alright, so when the plane is approaching, the angle there increases and the relative velocity decreases, and therefore the frequency that Kevin hears will gradually decrease as well, because the amount of the plane is approaching Kevin, the frequency Kevin hears will be higher than the actual frequency. However, the amount that's higher by is it's depending on the speed of the source, the relative speed of the source. Because the relative speed of the source is decreasing, therefore the observed frequency also decreases along with it. So as the plane is approaching, Kevin will hear a high frequency that begins to decrease as the plane flies closer. So here's a very challenging question here. So very, very challenging question. So give it a try. So Kevin walks into an apartment building, leaning on the balcony with his phone. As his phone vibrates, he is startled and drops his phone, which is vibrating at 900 Hz. Sometime later, he measures a frequency of 850 Hz. At the same time, a friend, Matthew, who lives in an apartment on the same level, across the street 60 meters away, records a frequency. Some more time later, Matthew records a frequency of 50 Hz lower than the frequency he first picked it up. Calculate the distance that the phone dropped during between the time Matthew recorded the two frequencies. So basically, I want you to find the distance the phone dropped. So when Matthew first recorded its first frequency, so when Kevin recorded a frequency of 850 Hz, Matthew recorded a frequency. Then sometime later, Matthew recorded another frequency that is 50 Hz less than the frequency he first recorded. So I want you to find the distance the phone drops in between the time between those 2 points. Alright, and here's a little bit of a diagram to help you out, okay? So as you can see, we have Kevin on the left building and we have Matthew on the right building. Just to let you know, this is not to scale, okay? So don't try to measure this for anything. This is not to scale. This is a little bit of a diagram to help you out here. And so what I want is a distance that the phone drops between its first point and the second point. So that distance there. Alright, so we know that Kevin hears an 850 Hz sound as the phone is moving directly away from him. So we know that when Kevin drops the phone is moving directly downwards, and in this case, the relative velocity is directly down, and the phone is moving directly away from Kevin. So therefore, we can directly find the velocity of the source, which is the phone, and we know that Kevin observes a frequency of 850 hertz. The actual frequency is 900 hertz, and we rearrange to find the speed of the source. And in this case, the speed of the source comes out to be 20 meters per second. So when the phone is moving at 20 meters per second downwards, we know that Kevin will hear a frequency of 850 hertz. So now Matthew is on the other building, okay? So because Matthew is on the other building, there's actually an angle between the phone and Matthew, and this means that the relative velocity isn't the same for Kevin and Matthew. For Matthew, the relative velocity will actually be the velocity in the same way the waves travel to Matthew. So in that diagonal component. Right, so the phone is moving at 20 meters per second, and we need to find the relative velocity to Matthew. To do this, we need to find the angle x, and we can find this by trigonometry. If we found the distance, we can find angle x if we can find the angle. Oh, sorry, what am I saying? We can find the angle x if we found the distance that the phone dropped in this time. So when the phone is dropped, it reaches a speed of 20 meters per second. That's when Kevin sees a frequency. Well, not sees. That's when Kevin hears a frequency of 850 hertz. And during this time, we can use kinematic equations to find out how much the phone dropped. In this case, we'll use Vf squared equals to Vi squared plus 2AD. If we substitute our numbers in, we'll find that our distance traveled, because gravity is acting downwards, is 9.81. So we know that our distance traveled is 20.387 meters. By our basic trigonometry, we know that tan x equals to 20.387 over 60. So that's our opposite over adjacent. And we'll get that our angle x is 18.77 degrees. So now, by vertically opposite angles, we can actually find the component of velocity that's in Matthew's direction. So the angle x is actually equal to the angle in that vector diagram as well, because of vertically opposite angles. So therefore, cos of 18.77 equals to V over 20, and therefore V equals to 18.936 meters per second. So this is the relative velocity of the phone to Matthew, and therefore we can use this velocity in our Doppler equation. So now we can find that what frequency did Matthew observe when Kevin observed a frequency of 850 hertz. And we can use that our Doppler equation. Alright, so we know that f dash equals to 900, our actual frequency, multiplied by 340 over 340 plus 18.936, because the component, the relative velocity component is still moving away from Matthew, therefore it's a plus sign. And we'll see that our observed frequency is 852.518 hertz. Alright, so we know the observed frequency now. After when Kevin heard a frequency of 850 hertz, Matthew heard a frequency of 852.518 hertz. So now we want to find when Matthew hears a frequency 50 hertz less. So first we'll take 852.518 minus 50, and that will be the frequency Matthew hears the second time. Okay, so Matthew hears a frequency 50 hertz lower on this next occasion. We can find the speed of the source relative to Matthew when this occurs. So that's the very key word, the speed of the source relative to Matthew. So if we take away 50, we'll get 802.518 hertz. And then we can use our Doppler equation to once again find the speed of the source relative to Matthew. That speed of the source is 41.3 meters per second. And that's just rearranging the equation. So hopefully you guys should all be comfortable with rearranging the equation for Vs, and we'll find that Vs is 41.3 meters per second. Alright, so some people might be tempted now just to use our kinematic equations to find our distance. However, one thing we cannot forget is that this is the component of velocity that's relative to Matthew. So that's that component of gravity. It's not the vertical component downwards, okay? This is the component of velocity that is in that diagonal direction, and that is the direction that the waves are traveling to Matthew. So that's a very key difference. So this Vs 41.3 meters is not our final Vs downwards. We still have more work to do. So now we need a simultaneous equation to solve in terms of angle y. Equation 1 can be found by using the final velocity downwards, such that cos y equals to V over Vf. So if we look at our vector diagram in our diagram, we'll see that cos of y equals to our v. So that's our relative velocity to Matthew. That's the v we just calculated is 41.3, and vf would be the final velocity downward. So that's the velocity we want to find out. So cos y equals to v over vf. Equation 2 can be found, found by using trig. So if we look at the triangle, so that right angle triangle, we can see that tan of y equals to 60 over, so that's the opposite side. The adjacent side would be the distance traveled in the first instance, which is 20.387 meters, plus the distance traveled between the two times, which is d. We'll call it distance d, and distance d is what we want to find as our final answer. Alright, so now our kinematic equations. Kinematic equations, Vf equals to V over cos y, and V equals to 41.3 meters per second. So we can use our kinematic equation. So Vf squared equals to 20 squared plus 2 times of 9.81 times of d. So once again, this d is the amount of distance traveled by the phone between the time when Matthew first heard a frequency of 852.518 hertz, and then it drops some distance as that Matthew heard a frequency of 802.518 hertz. So that's the distance drop, that's our d, and that d value is what we're trying to find. But we know that Vf equals to V over cos y as from our equation 1, and we can substitute Vf as V over cos y, and we know V is 41.3 meters per second, so 41.3 squared over cos squared y equals to 400, that's 20 squared, plus 19.62 d. So that's our equation number 1. Equation number 2, equation number 2 is tan y equals to 60 over 20.387 plus d. So that's our equation 2. So now we need to use a little bit of trigonometry identities. So cos squared y is equal, so 1 over cos squared y is equal to secant squared y. So we can substitute 1 over cos squared y with secant squared y. So 41.3 squared times secant squared y equals to 400 plus 19.62 d. However, we know that tan squared y plus 1 equals to secant squared y. That's from our trigonometry identities. So therefore, we know tan y is 60 over 20.387 plus d. So therefore, we can replace secant squared y in our equation by tan squared y plus 1, which is 41.3 squared multiplied by 60 over 20.387 plus d whole thing squared plus of 1, and that equals to 400 plus 19.62 d. Alright, so now we have two equations in terms of d. So now we can just fully simplify the equation with d, and we can rearrange to find d. Because we have no other variables, we can just use a little bit of algebraic manipulation. So we need to square it, and then we need to we divide both sides by 41.3 squared, and then we multiply both sides by the denominator, and then we subtract both sides by 360, and then we'll complete the cubic equation. So at this stage, you can just use your calculator. So cubic, so your degree will be 3. Our highest degree is 3d cubed. So now we substitute our values, and we should find that our d value is 47.5 meters. And that should be our final answer there. So the phone drops another 47.5 meters, and then Matthew hears a frequency 50 hertz lower than the frequency he first heard. Alright. So that should be our final answer. 47.5 meters. Okay, so very difficult question here. So this is a very challenging question. This probably won't show up in the exam, but it's just a very good question to get us thinking. And this is a challenging question. Okay, so don't be upset if you didn't get this question correct or you struggled with this question. It's very difficult question, and just as long as you understand how it works now, it will be good. Alright, so we have a final question here. So afterwards, Kevin and Matthew meet up to discuss the frequencies they recorded. They find that Matthew's recorded frequency were always higher than Kevin's recorded frequency at that same time. So when the phone dropped a certain distance, they both recorded a frequency. Matthew's frequency was always higher than Kevin's frequency, and they deduced that the devices are not working. So this question asks you to explain why they are wrong. Alright, so in this case, the reason that Kevin's recorded frequency is always lower than Matthew's recorded frequency is because the relative velocity of the phone to Kevin, so that will just be the directly downwards. It'll be directly downwards velocity. That will be the relative velocity of the phone to Kevin. However, the relative velocity of the phone to Matthew, that would be a component of velocity, or a component of velocity acting in in the direction of Matthew. This component of velocity is always smaller than the component of gravity downwards due to the component downwards that Kevin observes is always lower, which means that the relative velocity to Matthew is always lower than the relative velocity to Kevin. Because the phone is moving away from Kevin and Matthew, that means the actual frequency heard would be lower than the true frequency. But because relatively the phone is moving because relatively the phone is moving slower away from Matthew than it is to Kevin, therefore the Matthew's frequency heard will always be higher than Kevin's frequency heard. Because to Kevin, the relative velocity of the phone is just the phone traveling downwards, and this relative velocity is always greater than the relative velocity the relative velocity that of the phone to Matthew. And because of this, Kevin will always observe a higher frequency than Matthew, no matter how far the phone falls and how fast the phone is. That component of velocity will always be smaller. Will always be smaller than the vertical velocity down, and that's because the relative velocity to Matthew is just the component of the velocity downwards, and that component of the velocity downwards is always smaller than the component downwards itself. And that's why the relative velocity to Matthew is lower, and hence the actual frequency observed by Kevin is always higher than Matthew. So that's what you really need to say for this final question. And I didn't actually write a full answer to this question, but hopefully my explanation was clear and you understand why Kevin always hears a higher frequency than Matthew. Alright, so I actually made a Doppler Effect quiz on the quiziz.com. So if you're interested and you want to have a little bit of practice before your exam, or maybe some practice before your topic test, then feel free to use the link in the description in order to access the questions, and you can invite a couple of friends and you can play it together. And you it does contain a couple of challenging questions, very challenging questions. But it's very good practice for those who want to get excellence at level 3 and for those who want to try to get the scholarship this year. So if you want a last minute exam revision or last minute topic test revision, I've left a link down to my quiz, and you can just invite a couple of friends over, or you can just revise by yourself. And that's it for this video. I hope you enjoyed the video, and I hope to see you guys in the next one. Thank you. Bye.